So moving along, composite functions and their domains. So now let's kind of put everything together. We've got f of x is 1 over x plus 3, g of x is 3 over x minus 2. First, find each of f of g and f of f in general. So just what is f of g of x? What is f of f of x? And then find the domain for each. Okay, so first try to find what the functions are, then find their domain. Okay, hopefully we give it a shot. So the domain of f is everything except for -3, and the domain of g is everything except for 2. This is a handy observation to make at the beginning before we start composing them together. So let's take a look at f of g. So I take g of x, which is 3 over x minus 2, and I plug it into f, which means I have 1 over the input plus 3. And now I have to start simplifying things down. So if you simplify this, what you could do to see how you go from here to here, I'll do it up here in this upper right corner. So we have 1 over 3 over x minus 2 plus 3. What I'm going to do is I'm going to multiply this by x minus 2 over x minus 2. Okay, so my numerator is exactly x minus 2. And when I distribute x minus 2 across this denominator, we get, so my numerator is x minus 2 over 3 over x minus 2 times x minus 2 plus 3 times x minus 2. So that was taking this x minus 2 and distributing it to each of these terms here. These x minus 2's cancel, and that's how we got this denominator there. If we simplify that down, we get x minus 2 over 3x minus 3. And then you could factor that 3 out from the denominator there. Sorry, let's go back. So here is f of g, right there. Now, if you got to this and then you said, now what's the domain? You might say, oh, it's just x can't be equal to 1 and call it a day, but there's more to it, okay? Because in order to investigate the domain of this composition, this composite function, I need to be in the domain of g, and then I need the output of that to be in the domain of f. And notice the domain of g prohibits x from being equal to 2. So the domain of g prohibits x from being equal to 2, so I cut that right out from the possible domain. But then I need the output of g to be in the domain of f. So our function was x minus 2 over 3 times the quantity x minus 1. This was f of g. Now, if you solved, g of x needs to be in the domain of f. Okay, sorry, I need to flip back to remind myself what f was. 1 over x plus 3. Okay. So I need g of x to be in the domain of 1 over x plus 3. In other words, I need g of x can't be equal to -3. That would be a problem. If you set g of x equal to -3, you'll see x can't be equal to 1. So this restriction, g of x needs to be in the domain of f, is exactly the same as this denominator not being equal to 0. Okay, I need to clear out my pen marks because there's more book writing on this slide. So we excluded 2 because that wasn't in the domain of g, and now we exclude 1 because that would make the output of g not in the domain of f. So the domain is everything except for those exclusions. Okay, how about f of f? Well, I take 1 over x plus 3, which was the function f of x, plug it into f, and I end up with 1 over the input plus 3. To simplify this, just multiply numerator and denominator by x plus 3, okay, which will cancel off this one down here, and then I'll need to distribute it across that one there. That's where this denominator is coming from, which simplifies down to the following. So now what's the domain? Well, I need to be in the domain of the first step, which was just the function f, so I can't have -3 in my domain. But then the output of that needs to be in the domain of the second step, which is also f. So I need 1 over x plus 3, the output, to not be -3. This would be the bad value to input to the second function, which happens to also be f. Okay, and if you solve this, 1 over x plus 3 is definitely not equal to negative 3. What you will find is x can't be equal to negative 10/3, which is exactly the same thing as not making that denominator of our composite function equal to 0. So overall, the domain is everything except for negative 3, because that can't be plugged into the first function f, but also not negative 10/3, because then the output of this could not be plugged into the second function, which is also f. Okay, so we can also see that by taking the composition, which had a denominator, so f of f, was something, I forget exactly what, but it was over 3x plus 10. And if I say, well, I don't want 3x plus 10 to equal 0, that's going to give me x can't equal negative 10/3, which is exactly what we had already found anyway. So that's the other way you can see that. Whoops, let me get that out of there. Okay, so two different ways of getting the same result. Let's do another example. I have two functions f of g. F of x is 2x minus 5, and g of x is x plus 5 over 2. Show that if I do the composition f of g, but if I also do the composition g of f, I get out the same thing. These two things are equal, and what I get out is just plain old x. So work through these compositions, do the relevant simplifications, and see that you get out the same thing. Okay, so let's work through it. Hopefully you've already given it a shot. So first we're going to take g of x and plug it into f. So I take x plus 5 over 2, that's g of x, and I plug it into f, which means multiply the input by 2 and then subtract 5. Notice the 2 over 2 is exactly going to cancel, and then the 5 minus 5 cancels, and we get just x, which is what we were hoping for. Now we just need to do the same thing for g of f of x. Okay, so take f of x, which is 2x minus 5, plug it into g, which says take the input, add 5, and then divide by 2, and then in the numerator, the negative 5s are going to cancel, and then the 2s are going to cancel, and we have just x, which is exactly what we wanted. Oh, sorry, the garbage truck is going by outside. So what we found is that no matter which way we compose them, f of g or g of f, we just get x. And notice the domain in both cases was going to be everything. Okay, so we had f of x is 2x minus 5, which the domain is everything, and g of x was x plus 5 over 2, and the domain of that is everything. So there's no possible badness of, say, f of x outputting something that isn't in the domain of g, because the domain of g was all real numbers. So the domain of both functions is all real numbers means that the composition has domain all real numbers. So this holds for every real number because it holds everywhere you could possibly do the computation. So let's, oh, by the way, so this sort of special scenario where f of g and g of f both produce just the x, this is a sort of special scenario that we'll take a look at again in a later section, which is why we're introducing it in an exercise here. Okay, two functions that compose with each other to produce such a straightforward result, that's handy. Okay, but let's take a different sort of problem. Here is an overall function. Capital H of x is 3x squared minus 5 to the 21st. There's no unique solution here, but can you find a function f and a function g so that if you compose them, you get out this? Okay, and so go ahead and try to do this. And I would actually say, if you manage to do it, try to find a different way to do it. So the most straightforward way to do it is that the function h has a sort of inner piece of 3x squared minus 5, and then it raises all of that to the 21st. So the most straightforward way is to say g of x is 3x squared minus 5, and then f of x is x to the 21st, because then what do? You take g of x, 3x squared minus 5, and you plug it into f of x, which was raise the input to the 21st. So overall, you get exactly what we wanted. I would point out this is not the only solution. For example, I could do g of x is equal to, how about x squared? And then f of x is 3x minus 5 to the 21st. Then what's f of g? Well, I'm going to take x squared and plug it into f, and I get 3x squared minus 5 to the 21st, which is the same thing. There was not going to be a unique solution here. Okay, you could even do some sort of weirder stuff. Whoops, I just knocked over my microphone. Sorry about that. Let me just fix this. So we could even do this in a weirder way, where we could do something like, let's let g of x be a 3x squared minus 5 to the 10th. Why not? So I could do the following. G of x is 3x squared minus 5 to the 10th. And then I can say f of x is x to the 21 over 10th power. It's a weird little function, but sure, why not? Then what's f of g of x? It would say, take 3x squared minus 5 to the 10th and plug it into the function f, which says take that input and raise it to the 21 over 10th power. One exponent raised to another means multiply them, and then the 10s would cancel, and I'd get exactly 3x squared minus 5 to the 21st. Again, same result, even with two different choices of f and g. So frequently there is a most obvious choice, and in this question, I think the most straightforward thing was what the book did exactly. 3x squared minus 5 is your inner thing, and exponentiating to the first is your sort of outer step, but that doesn't mean it's the only correct answer. So let's do another, okay? Find functions f and g so that what you get out when you compose them is 1 over x plus 3. So again, try to come up with 1. Check that when you compose your two functions, you get out 1 over x plus 3. And if you found that pretty straightforward, see if you can't come up with something else that does the same thing. So the most straightforward way is to do your two pieces are x plus 3, and the other is 1 over x. So then if I had g of x as x plus 3 and f of x as 1 over x, I would just take x plus 3 and plug it in and get 1 over x plus 3. So an alternate way that you could do this, maybe g of x isn't x plus 3, it's x plus 2. But then f of x is 1 over x plus 1. Then what's f of g of x? Well, we would take x plus 2 and plug it into f, which says 1 over the input plus 1, and now I have 1 over x plus 3, just like we wanted. So again, we can see there's not a unique solution here. There's many ways we could do this. Okay, so that's the end of section 2.1. So come on back for section, 5.1. So come on back for section 5.2.